Hey everyone, and welcome. In the next few minutes, we're going to blitz through everything you need to know about heat transfer. Let's get this revision session started.
So, let's kick things off with a simple question to get our brains warmed up. Ever really thought about this? Well, the science behind it is exactly what we're covering today.
Okay, let's dive right in with a super fast recap of the 3 most important rules about heat. If you remember these, you're already halfway there. First up, this is the golden rule. Heat is always a one-way street. It flows from hot to cold, never, ever the other way around, until everything evens out. Rule number 2 is all about what heat does to stuff. Just remember, heat makes things get bigger, and cold makes them get smaller. It's because the particles inside are either getting all energized and spreading out, or they're losing energy and bunching up. And finally, rule number 3. These are the big 3 ways heat gets from A to B. We're about to break each one down, and understanding them is totally key to acing this topic.
All right, let's get into the basics. We're going to make sure we've got the fundamentals locked down, starting with temperature, expansion, and contraction.
Okay, this is a classic, right? We use these words all the time, as if they mean the same thing. But in science, nope. They're 2 very different things. Do you remember what they are? So here's the deal. Temperature is just a measurement, a number you'd see on a thermometer. But heat is the actual energy that's on the move from one object to another. We know heat makes things expand, but where do we actually see this happening? Well, it turns out it's pretty much everywhere you look. I mean, this one single principle affects everything. Engineers have to leave gaps in railway tracks to stop them from buckling in the summer sun. It happens on a massive scale with our oceans, and it happens in something as simple as the air inside a balloon. It's pretty amazing.
Awesome. Now for the main event, the 3 ways heat gets around. This is the absolute core of our revision.
Let's start with conduction. And yep, think right back to that metal spoon we talked about at the beginning. The reason it gets hot is all down to this.
So, conduction is just heat transfer through direct touch. In solids, particles vibrate and literally bump into their neighbors, passing the energy along. This works incredibly well in metals because their particles are packed super tight. That's why they're good conductors. But in things like wood or plastic, the particles are more spread out, which slows the heat right down. We call them insulators.
Okay, on to method number 2, convection. Now this one is all about movement. It doesn't happen in solids. It's all about liquids and gases, what scientists call fluids.
So, anytime you watch water boiling in a pot, you're seeing convection. The hot water at the bottom gets less dense and rises up. The cooler, denser water from the top sinks down to take its place, gets heated, and rises too. This creates a cycle, this amazing circular flow called a convection current.
And now for our final method, radiation. So, wait a second. Conduction needs touch, and convection needs flowing fluids. But space is empty, right? A vacuum. So how on earth does the sun's heat travel all the way through nothing to reach us?
And that's the magic of radiation. It travels as infrared waves. And the key thing, the really unique thing, is that it doesn't need any particles to travel through. It can beam right across a vacuum, which is why we feel the sun's warmth from millions of miles away.
This table is the perfect summary. Just lock this in. Conduction is through direct touch, so it's best in solids. Convection is the movement of fluids, so that's for liquids and gases. And radiation is the special one, heat traveling as waves, which works best in empty space. Got it? Perfect.
Okay, now for the really cool part, heat transfer in action. Let's see how all this science gets used in the tech we use every single day.
This is such a clever use of that expansion principle we talked about right at the start. It's brilliant, practical physics. So check this out. Inside, there's a bimetallic strip. That's just 2 different metals fused together. As it gets hot, one metal expands more than the other, which forces the whole strip to bend. As it bends, it physically breaks an electrical contact, which cuts the power. It's a simple, automatic off switch powered by heat itself.
Okay, final challenge. Think of something you use all the time to keep drinks hot for hours or cold for hours. What's designed to stop all 3 types of heat transfer at once?
It's the vacuum flask. This thing is a masterpiece of thermal engineering. The shiny surfaces reflect heat radiation. The vacuum between the walls has no particles, so it stops both conduction and convection. It literally tackles all 3 methods at once. It's the ultimate defense against heat transfer.
So there you have it. You've got the science down. Now, how would you use it?
Think about it. If you were designing the perfect winter coat, what materials would you use and why? How would you stop conduction, convection, and radiation? That's your challenge. You've done a great job with this revision. Well done.